Welcome back. We're going to continue our adventure in chapter 9, where we left off learning about the integral test and the applications of that. And now we're going to move forward into 9.4, and we're going to talk about comparison of series. And so the idea here is, are we given a series that is comparable or similar to a series that we understand? The series that we understand are telescoping, geometric, and p-series. Now, for the sake of our discussion, telescoping is not going to be an option. Either you're telescoping or you're not, either you cancel terms or you don't, and so you can't really be similar to telescoping, right? You're either telescoping or you're not. However, you can be similar to geometric series. You can be similar to an exponential function in format. You can be similar to a 1 over n to the p in format. And so those make sense to talk about with comparison. And so first we're going to look at what we call direct comparison. Now, this type of comparison is very direct. It's very straightforward. It's a nice, easy kind of test to understand and to run, but it's not necessarily useful in a lot of cases. It's a very, very specific situation. And so say we're given two positive sequences. Very important that they're positive. We have no negative outputs of sequences yet. We're dealing with here, right? So positive sequences, so bigger than 0. But we have that, say, a sub n is less than or equal to b sub n. And so the outputs of the A sequence are always smaller than or equal to the outputs of the B sequence. And well, what does that mean? If all the terms are smaller or larger than another, we get some relationship between convergence, or when we go to sum up those terms. Specifically, if the A sub n terms, if those terms diverge or blow up to infinity when we add those up, well, my B sub n terms are always larger than A sub n terms, and so of course when I would add up these terms, they would also then diverge. So if I'm larger than something that diverges, I would also have to diverge. So that's one comparison we have. Either we want our sequence to be larger than a sequence that diverges as a series, or the flip side of that would be, okay, well, say the larger thing converges, say B sub n converges. The sum of the terms of this sequence spit out something finite for me, and A sub n is smaller or equal to that sequence. Well, if all the terms are smaller than all of these terms, then when I go to add up the smaller terms, they will have a smaller value than the larger ones. So if B sub n converges and gives me something finite back, this would also have to give me something finite back. So again, the idea here is, in this case, we want to be smaller than something that converges as a series. So either we want our sequence to be smaller than a sequence that converges as a series, or we want our sequence to be larger than a sequence that diverges as a series. So larger than a divergent series or smaller than a convergent series. That is the name of the game. And we can play this game with some simple types of examples. And so in this case, we have 1 over n squared plus 2. Now, if you look at 1 over n squared plus 2, we have to be able to determine, okay, well, what is it comparable to? Can I say it's bigger or smaller than something that I understand? And in this case, if you think about it for a second, if I get rid of that 2, it's a p-series. Now, the only thing that to be careful of is, in getting rid of that 2, does it make me bigger or smaller? And so larger denominator means a smaller fraction. And so if I get rid of the 2, I've created a larger number. This is a bigger denominator, so a smaller fraction. So 1 over n squared plus 2 is less than or equal to 1 over n squared. So that's the comparison that I would get. And fortunately for me, we know that this series converges. We just talked about p-series. And so it falls into this scenario. It says, okay, we have this inequality, and look at that. The larger thing converges, and so the smaller thing would also have to converge, which is my series. And so by direct comparison, we can say that this series converges. Now, in the same way, we can look at the next one, 6 to the n minus 1 over 5 to the n. Okay, well, it's not a geometric series. It's very close to geometric, right? Exponential. In fact, if I get rid of that 1, it is geometric. Okay, well, what would getting rid of that 1 do? It would create this, 6 to the n over 5 to the n, but getting rid of the 1 in the numerator, would that make me larger or smaller? Just think. Subtracting from the numerator makes you a smaller number. Subtracting from the numerator makes you a smaller number. So of course, then this guy would be less than or equal to 6 to the n over 5 to the n. Because I've subtracted one from the numerator. So if I add one back, I've made myself a larger number. So this is larger. And now we have an issue. And so let's fix the issue before we get into the ones where I won't fix the issue, then we'll have to do something else. Let's say we had it this way. Now I can't do this in general. But let's say I just fixed a problem and I do this. Well, now adding one, that's larger. So then we have an inequality that goes this way. 6 to the n over 5 to the n is smaller than 6 to the n plus 1 over 5 to the n. Why do I need the inequality to go this way? It's because, well, if we look at the series 6 over 5 to the n, this is a divergent geometric series. If the inequality was going the other way, I wouldn't know what to say. I would say, okay, well, b sub n diverges and I'm smaller than it or equal to it. So either I could diverge or I could converge. So I can't really get an answer. However, in this case, now we can. It worked out great because my sequence is larger than this sequence. And since now I'm larger than a sequence that diverges as a series, then this series must also diverge. Now, I brought up this example to illustrate the fact that direct comparison is not easy to do, right? It needed to be plus 1. If I had that minus 1 there, I get an inequality, but it wouldn't be the inequality that I need. I either need to be larger than something that diverges or smaller than something that converges. Now, in that case, it didn't work, so I just fixed it because I'm in charge of the whiteboard. But if I wasn't allowed to fix it, then we run into an issue. For example, here, 1 over n plus 1, I could easily say that this is less than or equal to 1 over n, but that doesn't help me because 1 over n as a series diverges, and I'm smaller than something that diverges, smaller or equal to something that diverges. So I could be infinity, I could be finite. I don't have an answer. In the same way here, right? I don't even know if I could write an inequality because a bigger denominator means a smaller fraction, a bigger numerator means a larger fraction, and so in this case, it's not even that I get an inequality. Can I directly relate this to 2 to the n over 3 to the n? I don't know. And so unless it's a very clear relationship and that relationship goes in the right way, we can't really use direct comparison. And so while direct comparison is a very nice and easy and straightforward test and can be used in certain cases, it's not in general the way to go. And so what we're going to do in the next video is we're going to talk about what we call limit comparison. Now, limit comparison is the better way to compare things because it gets to the heart of really where divergence and convergence happen, which is at infinity. Because if I asked you to add up the first 1,000,000 terms of a series, of course it's a finite number. If I asked you to add up the first 2 billion terms of a series, it's a finite number. Any series, right? If I only asked you to add up the first 2 billion terms, you'll always get something finite. It might take you a while, but it's finite. So where does this infinity or this divergence happen? It happens at infinity anyway. And so I really only care about comparing series at infinity. I don't necessarily care about comparing the first 20 terms, or the first 200 terms, or the first 200,000 terms. I don't necessarily need this to be true for all n. I really only care of what's happening at infinity. And so let's talk about comparison at infinity, because that's where the divergence and convergence is really determined. And so in the next video, we're going to look at what we call limit comparison. Now, limit comparison is comparing via a limit, right? A limit at infinity. And that's going to give us a nice way to talk about comparison where we don't have to worry about getting the right inequality in the right way with the right series. It gives us a little bit more room to work, a little more wiggle room. And so that's going to be the next video, limit comparison.